There is a predator in the skies that is at once a masterpiece of raw aerodynamic engineering and a magnificent, terrifying fossil. It is the absolute zenith of a dying breed, the final, brutal expression of the conventional fourth-generation fighter. This is the Sukhoi Su-35S, known to NATO as the Flanker E, an aircraft that represents the last true brawler in an age of invisible, networked assassins. It is an ultra-maneuverable air killer, a machine defined by a triad of capabilities: extreme agility from three-dimensional thrust vectoring, a powerful sensor suite built on a philosophy of brute force rather than finesse, and a massive weapons payload that allows it to hunt anything that flies. If you're enjoying this breakdown of one of the most formidable fighters ever built, hit that like button and subscribe for more in-depth aircraft analysis. And let me know in the comments, which aircraft should I cover next? But to understand this aircraft is to understand its complex, two-part history, a story of Soviet ambition, post-Cold War collapse, and pragmatic resurrection. The designation Su-35 itself is confusing, as it has been applied to two fundamentally different aircraft. The first Su-35, born in the 1980s as the Su-27, was the original Soviet superflanker. It was a technology demonstrator intended to be the ultimate evolution of the Su-27, distinguished by the addition of canard foreplanes and an upgraded, albeit primitive, multifunction radar. About 12 to 14 of these were built, including one which was further modified with early thrust vectoring nozzles and redesignated the Su-37, the star of many 1990s airshows. This entire program, however, collapsed along with the Soviet Union, a victim of catastrophic budget cuts. The name lay dormant until 2003, when Sukhoi resurrected it. But the new aircraft, which would fly in 2008 and eventually be designated the Su-35S, was a different beast. This deep modernization was not a mere update, but a pragmatic and comprehensive redesign, born of necessity. It was intended as an interim fighter, a stopgap to bridge the yawning capability chasm as Russia's fifth-generation fighter program struggled with delays, cost overruns, and technological hurdles. This new Su-35S was designed to keep the Komsomolsk-on-Amur aircraft plant production lines running and to generate critical export revenue. It was a brilliant marketing move, labeling the aircraft as 4++ generation. This term, a piece of marketing genius, implied a machine that transcended all existing fourth-generation platforms and nipped at the very heels of fifth-generation stealth fighters. In many ways, the Su-35S was the Su-57 program's practical testbed. It matured the engines, radar concepts, and flight control philosophies that the Su-57 itself was not yet ready to field, ironically becoming a far more successful, numerous, and strategically important aircraft than the fifth-generation platform it was meant to precede. The airframe itself, while visually an evolution of the iconic Su-27, is structurally a different machine. Built at Komsomolsk-on-Amur, the design underwent a deep modernization with a strengthened structure to handle a significantly higher maximum takeoff weight of 34.5 metric tons and the extreme gravitational loads of its new maneuvering capabilities. The designers made a critical internal change. They increased the internal fuel capacity by over 20% to a massive 11,500 kilograms, partly by using the wing torsion boxes as fuel tanks. This gives the Su-35S its enormous operational range of 3,600 kilometers on internal fuel alone, dwarfing most of its Western counterparts and allowing it to function as a long-range patrol and interdiction asset. To manage fuel slosh during the violent, high-gravitational maneuvers the aircraft is capable of, the tanks are filled with a spongy polyurethane foam. The airframe also sees a much higher percentage of advanced materials, with an increased use of lightweight titanium alloys, a traditional strength of Russian aerospace metallurgy, and carbon fiber composites, especially in the horizontal and vertical stabilizers and wing surfaces. This helped to keep the weight of the reinforced, enlarged airframe in check. While not a stealth aircraft by any measure, some measures were taken to reduce its radar cross-section. These include the application of radar-absorbent materials at critical points like the engine inlets and the leading edges of the wings, and a special conductive coating on the cockpit canopy to deflect radar waves. These efforts reportedly reduced the aircraft's frontal radar signature to between 1 and 3 square meters, a significant improvement over the original Su-27's flying barn signature, but still orders of magnitude larger than any true stealth design. Perhaps the most telling design choice, however, was an act of addition by subtraction. The Su-35S deleted the canard foreplanes that had been the defining feature of the original Su-27M. This decision was not a regression, but a sign of supreme confidence in two new integrated technologies: a revolutionary flight control system and the engines that would become the heart of the Superflanker legend. Those engines are the twin Saturn AL-41F-1S, also known as the Izdelie 117S. It is important to note that these are not the mythical next-generation engines from the abandoned Soviet program, but rather a deep modernization of the proven engine that powered the Su-27. This modernization is extensive, featuring a larger fan diameter, new high and low-pressure turbines, and a fully digital control system that integrates them with the airframe. The result is a massive increase in power. Each engine produces 8,800 kilograms of dry thrust and a staggering 14,500 kilograms, or 32,000 pounds, with afterburner. With a typical combat load, this gives the Su-35S a thrust-to-weight ratio comfortably exceeding 1.1 to 1, allowing it to accelerate aggressively in a vertical climb. This raw power also enables a limited supercruise capability, allowing the Su-35S to sustain supersonic flight at speeds of Mach 1.1 or higher without the use of its fuel-guzzling afterburners, a significant tactical advantage that increases engagement range and reduces reaction time. The S in 117S, however, stands for the swiveling nozzles. These are the physical mechanism for the aircraft's three-dimensional thrust vectoring control. These nozzles can move independently to direct the engine's thrust, providing phenomenal control moments that are entirely separate from the aircraft's aerodynamic surfaces. But this hardware is useless, a mere curiosity, without the brain to control it. That brain is the KSU-35, a quadruple redundant digital fly-by-wire system. This integrated flight control system is the true secret of the Su-35S. It seamlessly blends the inputs from the pilot stick with the movement of the traditional control surfaces, the rudders, flaperons, and stabilators, and the thrust vectoring nozzles. It is this total integration that rendered the canards obsolete. The flight control system and thrust vectoring provided such extreme control authority, especially at low speeds where aerodynamic surfaces become mushy and ineffective, that the canards became redundant weight and aerodynamic clutter. This perfect fusion of airframe, flight control system, and propulsion unlocks the capability that defines the Su-35S in the public imagination: super maneuverability. This is the aircraft's ability to maintain full control in post-stall flight regimes, where the angle of attack is so high that the wings are no longer generating lift. This is where the airshow stopping maneuvers are born. Pugachev's Cobra, a dynamic deceleration where the aircraft pitches up past 90 degrees. The Herbst maneuver, a high angle of attack turn, and the Frolov Chakra, a seemingly impossible, flat, tight radius turn where the aircraft rotates on the spot. These maneuvers allow the Su-35S to decouple its pointing vector, where its nose and weapons are aimed, from its velocity vector, where the aircraft is actually going. It is a breathtaking display of engineering, a maneuver that seems to defy the laws of aerodynamics. It is also, in a real multi-ship engagement, a potential get-me-killed-immediately button. The tactical utility of these post-stall maneuvers is one of the most intense debates in modern aerial combat. The Russian doctrine, articulated by Sukhoi's own test pilots, argues that in a prolonged, merged dogfight, both aircraft will inevitably bleed energy. At low speed, a conventional fighter is a sluggish victim. The Su-35S, however, can use its thrust vectoring to perform a 3-second turn, pointing its nose and its short-range infrared missile seekers at an opponent who physically cannot follow. It's a last-ditch weapon for a close-in knife fight. The dominant Western and particularly American energy maneuverability theory views this as a suicidal gimmick. Performing a Cobra in combat dumps all of the aircraft's kinetic energy, leaving it at near-zero airspeed. While the first opponent might be fooled and overshoot, his wingman, or any missile that wasn't spoofed, now has a non-maneuvering, high-infrared signature target hanging in the sky. It is a 1 versus 1 dueling move in a 100 versus 100 networked battlefield. In all likelihood, both doctrines are correct. Super maneuverability is a terrible idea in a beyond visual range, missile-dominated battle. But in the one specific desperate scenario where a pilot finds himself in a low-speed, high-alpha merge, it provides a lethal asymmetric advantage. The question is whether modern air combat ever allows that scenario to happen. To find its targets long before such a merge occurs, the Su-35S relies on a sensory suite built on a philosophy of brute force. The primary sensor is the N035 Urbis-E, or Snow Leopard, radar. This is a massive, powerful X-band passive electronically scanned array radar. Its passive electronically scanned array architecture is a critical distinction. It is not an active electronically scanned array, which is the standard for all of its modern 4.5 and 5th generation competitors. An active electronically scanned array uses thousands of tiny independent transmit and receive modules, making it more resilient, harder to jam, and harder to detect. The Urbis-E's passive system, technologically simpler, instead compensates with sheer, unadulterated power, boasting a colossal peak power output of 20 kilowatts. This raw power, combined with its large 900mm diameter antenna, gives it a massive power aperture product. This is what enables the headline-grabbing 400-kilometer detection range, a staggering figure that is, to put it mildly, situationally dependent. That 400-kilometer range is only achievable in a very narrow queued search mode, against a large 3-square-meter target, which means an early warning aircraft or ground control has to tell the pilot exactly where to look. In a normal wide-area unqueued search, the realistic range drops to a still impressive 200 kilometers. Against a very low observable stealth target like an F-35 with a radar cross-section of 0.01 square meters, that detection range plummets to an estimated 50 to 90 kilometers, well inside the F-35's own weapons envelope. The Urbis-E can track up to 30 targets and engage up to 8 simultaneously when using active radar missiles, a very respectable capability. The problem is that its brute force passive nature makes it a phenomenal electronic beacon. Any adversary with a modern radar warning receiver will detect the Urbis-E's high-power emissions from hundreds of kilometers away, long before the Su-35S itself gets a return. Furthermore, unconfirmed but credible reports from Egyptian tests against the French Dassault Rafale claimed that the Rafale's electronic warfare suite could effectively blind and jam the Urbis-E, highlighting a passive electronically scanned array's inherent vulnerability to modern electronic attack. Complementing this loud radar is the silent OLS-35 optical locator system. This is the glass bulb forward of the cockpit, an infrared search and track system designed to passively scan for the heat signatures of enemy aircraft, making it the Su-35S's theoretical stealth hunter. It has an advertised detection range of 90 kilometers from the target's rear hemisphere and includes a laser rangefinder to provide targeting solutions for a cannon or unguided rockets at distances up to 20 kilometers. However, the OLS-35 possesses a critical and widely critiqued flaw. It is a non-imaging infrared sensor. This is essentially 1980s technology pioneered on the original Su-27 and MiG-29. A non-imaging sensor is a simple spot detector, and as a result, the OLS-35 can only track a maximum of 4 targets. By contrast, a modern imaging infrared search and track system, like the Eurofighter Typhoon system, creates a detailed thermal picture of the battle space and can track 500 targets simultaneously. This disparity has led some analysts to label the OLS-35 as the least capable infrared search and track system on any modern fighter. Another example of the Su-35S polishing a legacy technology to its absolute limit, just as the rest of the world moved on. For defense, the aircraft relies on the integrated Kibini-M electronic countermeasures suite. This system is designed to jam enemy radars and, most importantly, the seekers of incoming active radar missiles. Reports from its use in Ukraine suggest it is effective at degrading older radar systems, but it has also been noted to cause electromagnetic interference with the Su-35S's own Urbis-E radar, a complex problem that fifth-generation sensor fusion solves, but which the Su-35S's federated, bolted-on avionics architecture still struggles with. Where the Su-35S truly earns its killer moniker is its arsenal. It features 12 hardpoints and can carry an enormous 8,000-kilogram payload. For last-ditch encounters, it retains the internal Gryazev-Shipunov 30mm autocannon. This is an engineering marvel of weight saving, weighing only 46 kilograms, yet it fires 30 by 165mm shells at a rate of 1,500 to 1,800 rounds per minute. Its limitation is its ammunition supply. With only 150 rounds on board, the pilot has roughly 5 seconds of trigger time. It is a weapon of extreme precision or extreme desperation. As a true multi-role platform, it can deploy a vast array of air-to-ground ordnance, including anti-radiation missiles for suppression of enemy air defenses missions, long-range standoff missiles, anti-ship missiles, and the full family of 500 and 1,500-kilogram television, laser, and satellite-guided bombs. But its primary role is air superiority, and its air-to-air armament is formidable. For dogfighting, it carries the R-73 or R-74, a classic, highly agile, all-aspect infrared missile paired with the pilot's helmet-mounted sight. For beyond visual range combat, its primary weapon has been the R-77-1, an active radar missile with a 110-kilometer range, making it a rough equivalent to the U.S. AIM-120C. More recently and more threateningly, the Su-35S has begun deploying the new R-77M, a significant upgrade with conventional fins replacing the R-77's high-drag lattice fins, a dual-pulse rocket motor, and reportedly an active electronically scanned array radar seeker, pushing its range to 200 kilometers and finally matching Western and Chinese counterparts. The Su-35S's ace in the hole, however, is the Wimpel R-37M, NATO codename Axehead. This is a colossal hypersonic weapon traveling at Mach 6 with a staggering 400-kilometer range. It was not designed as a fighter killer, it was designed as an early warning and control system killer, a long-range sniper rifle to destroy high-value, low-maneuverability assets like tankers and surveillance aircraft from far outside the range of their fighter escorts. In a theoretical matchup, the Su-35S presents a complex challenge. Against its 4.5-generation European rivals, the Eurofighter Typhoon and Dassault Rafale, it's a brawler versus boxer scenario. The Su-35S, with its thrust vectoring, would almost certainly win a low-speed, post-stall, within visual range merge. The Typhoon, with its lighter airframe, superior high-speed kinematics, and vastly better imaging infrared search and track system, is designed to win the beyond visual range shoot and scoot engagement. The Rafale, meanwhile, plays a different game entirely, with its advanced electronic warfare suite and sensor fusion, which, as the Egyptian tests suggested, could allow it to win the electronic fight before the first missile is even fired. The most direct comparison is to the American F-15EX Eagle II, itself the ultimate modernization of a legendary Cold War airframe. Both are massive, twin-engine, non-stealthy missile trucks. But their differences reveal their core doctrines. The F-15EX is designed to win the beyond visual range fight with its superior active electronically scanned array radar, its imaging infrared search and track system, and its deeply integrated world-class electronic warfare suite. The Su-35S, with its passive electronically scanned array radar and thrust vectoring, is designed to survive the beyond visual range fight and win the within visual range merge. Against true fifth-generation platforms like the F-22 Raptor and F-35 Lightning II, the Stealth Hunter claims are exposed as a fantasy. A fifth-generation fight is about information dominance. The F-35's stealth and sensor fusion mean it will detect the Su-35S, a large, hot, electronically loud target, from hundreds of kilometers away. The Su-35S, with its less advanced sensors, will not detect the F-35 until it's inside 90 kilometers, by which point the Su-35S pilot has likely already been killed by a missile fired from a plane he never knew was there. The Su-35S's real-world combat record is a tale of two different wars. Its first deployment was to Syria in 2016, flying from Khmeimim Air Base. This was a low-intensity conflict. The Su-35S flew high-altitude air patrols and escorted bombers, facing no peer-level aerial threats. The deployment was an invaluable proving ground, allowing the Russian aerospace forces to test engine reliability, which was reported as high, and refine its avionics software. Most importantly, it was a marketing success, a showcase for potential export customers. The war in Ukraine, however, has been a brutal reality check. This is the first time the aircraft has faced a modern, dense, and integrated air defense network. Its performance has been a story of stark successes and fatal flaws. In its intended role, flying high-altitude combat air patrols deep inside Russian-controlled airspace, it has been lethally effective. Using its powerful Urbasi radar and its long-range R-37M missiles, Su-35S crews have successfully sniped numerous Ukrainian fighters who lacked the sensors to detect the launch or the kinematics to escape the massive weapon. It has also been a primary platform for suppression of enemy air defenses missions, firing anti-radiation missiles. But the Russian aerospace forces have failed to achieve air superiority, and the Su-35S's fatal flaw has been exposed. It is not stealthy. When forced to fly lower and closer to the front lines to deliver shorter-range munitions, it is hideously vulnerable. Visually confirmed lost databases have documented at least 8 Su-35S fighters as destroyed. For a top-tier, low-volume asset, this is a staggering loss rate. The war in Ukraine has reinforced a brutal lesson. In a peer-level conflict, the greatest threat to a fourth-generation fighter is not another fighter. It is the ground-based surface-to-air missile, and agility is no defense against a networked missile. Today, the Su-35S remains the backbone of the Russian aerospace forces, the high-end bridge that fills the capability gap left by the agonizingly slow and low-volume production of the Su-57. The most obvious and necessary modernization, an upgrade to a genuine active electronically scanned array radar like the one from the Su-57, is now likely a technical and industrial impossibility. Integrating an active electronically scanned array is not a plug-and-play swap. It requires a complete overhaul of the aircraft's power, cooling, and data processing architecture. More critically, Russia's domestic electronics industry has long relied on foreign-sourced high-end microelectronics for active array development. The severe international sanctions imposed post-2014 and especially post-2022 have severed this supply chain, likely freezing the Su-35S's sensor technology in time. The Su-35S is, therefore, a magnificent, lethal, and tragic machine. It is the ultimate expression of the Su-27 flanker, an evolutionary dead end that pushes fourth-generation kinematic and brute force sensor philosophies to their absolute physical limits. It is a king killer from a bygone era, a brawler perfected at the exact moment the fight became invisible, digital, and networked. It is the last and greatest of the superflankers, and we will likely never see its kind again. Yet the story of the Su-35S is not merely one of technological accomplishment and tactical limitation. It is also a mirror reflecting the deeper strategic dilemmas of the Russian military-industrial complex in the 21st century. The aircraft exists in a peculiar temporal paradox, a machine built with one foot planted firmly in the Soviet past and the other reaching desperately toward a future that may never arrive. Consider the industrial ecosystem that sustains it. The Komsomolsk-on-Amur aircraft plant, located in Russia's remote Far East, nearly 7,000 kilometers from Moscow, is one of the last remaining Soviet-era aerospace manufacturing centers still operating at scale. During the Cold War, this facility was deliberately positioned far from potential NATO attack routes, a geographic insurance policy against nuclear annihilation. Today, that geographic isolation has become both a blessing and a curse. The plant is insulated from the immediate chaos of Western Russia, yet it struggles with chronic labor shortages as young engineers flee to Moscow or emigrate entirely, seeking better opportunities in a globalized world that Russia is increasingly cut off from. The production rate of the Su-35S reflects these constraints. At its peak, the plant delivered approximately 12 to 15 aircraft per year, a respectable figure by Russian standards, but laughably inadequate compared to the industrial output that sustained the Soviet Air Force during the Cold War, when hundreds of fighters rolled off assembly lines annually. The export dimension of the Su-35S story reveals even more about Russia's strategic predicament. The aircraft was explicitly designed with foreign sales in mind, a revenue stream meant to subsidize domestic procurement and keep the production lines viable. China became the first and most significant customer, ordering 24 aircraft in 2015 for approximately $2 billion. This sale was celebrated in Moscow as a validation of Russian engineering prowess, but it contained the seeds of a strategic defeat. Chinese engineers meticulously reverse-engineered every system they could access, and within 5 years, China's domestic Shenyang J-16 fighter emerged as a near clone of the Su-35's airframe, powered by Chinese engines and equipped with indigenous active, electronically scanned array radars and electronic warfare systems that, in some respects, surpassed the Russian originals. China, once Russia's most lucrative export market for advanced fighters, has now become a competitor, offering its own fourth-plus generation platforms to the same developing nations that Russia once dominated. The bitter irony is that Russia, by selling its most advanced conventional fighter to China, essentially funded the development of its own obsolescence in the global arms market. Egypt, Indonesia, and Algeria have also expressed interest or placed orders for the Su-35S, but each deal has been complicated by the specter of American sanctions under the Countering America's Adversaries Through Sanctions Act, known as CAATSA. This legislation, enacted in 2017, specifically targets nations that purchase significant military equipment from Russia, threatening secondary sanctions that could cripple their access to Western financial systems and technology. Indonesia, which initially signed a contract for 11 aircraft, has repeatedly delayed deliveries, clearly unwilling to jeopardize its relationship with the United States and its access to Western defense systems for the sake of a single fighter type. Egypt, despite reportedly receiving several Su-35S aircraft by early 2020, has kept them suspiciously quiet, likely storing them in hangars to avoid provoking Washington while Cairo negotiates for American F-15s. This geopolitical stranglehold has transformed the Su-35S from a potential export cash cow into a strategic liability, a symbol of Russia's shrinking sphere of influence and its inability to shield its customers from Western economic coercion. The Su-35S also illuminates a fundamental philosophical divide in modern fighter design. Western air forces, led by the United States, have bet their futures on stealth, sensor fusion, and network-centric warfare. The F-35, despite its troubled development history, embodies this philosophy. It is not the most agile fighter, nor does it have the longest range or the biggest payload. What it possesses is information dominance. An F-35 pilot sees the battle space in a way that is fundamentally different from a Su-35S pilot. Every radar return, every infrared signature, every data link message from friendly aircraft, satellites, and ground stations is fused into a single, coherent picture displayed on the pilot's helmet-mounted display. The F-35 is not a fighter. It is a node in a distributed sensor network, a flying quarterback that can kill you, guide a missile from a friendly bomber, or simply pass targeting data to a surface ship hundreds of kilometers away. The Su-35S, by contrast, represents the perfection of an older paradigm. It is a platform designed to succeed through superior kinematic performance, raw sensor power, and overwhelming firepower. It is the philosophy of the gunslinger, the ace pilot, who wins through skill, courage, and a faster draw. In the abstract, both philosophies have merit. In practice, the networked, information-dominant approach has proven devastatingly effective in every conflict since the first Gulf War in 1991, while the kinematic, pilot-centric approach has increasingly been relegated to airshow demonstrations and nostalgic tributes to the fighter pilots of the past. There is also a human dimension to the Su-35S story that is often overlooked in technical analyses. The pilots who fly this machine are not faceless automatons. They are highly trained professionals, many of them veterans of Syria, who have developed genuine affection for the aircraft's capabilities and quirks. Russian pilots speak reverently of the Su-35S's responsiveness, the way the thrust vectoring nozzles allow them to point the nose with an almost telepathic immediacy, the raw, visceral power of the engines pushing them back into their seats during a combat climb. They also speak more quietly of their frustrations. They know that their radar, for all its brute power, is a liability against a modern adversary. They know that the Urbis E's high-power emissions are a neon sign in the electromagnetic spectrum, announcing their presence to any enemy equipped with a basic radar warning receiver. They know that the OLS-35, their so-called stealth hunter, is functionally blind compared to the imaging infrared systems on Western fighters. And they know, though few will say it aloud, that in a true peer-level conflict against a NATO air force equipped with F-22s and F-35s, their odds of survival are disturbingly low. This knowledge breeds a peculiar fatalism, a sense that they are flying a magnificent machine into a battle it was never truly designed to win. The future of the Su-35S is, in many ways, already written. Barring a geopolitical miracle that lifts sanctions and restores Russia's access to cutting-edge Western microelectronics, the aircraft will never receive the active electronically scanned array radar upgrade it desperately needs to remain competitive. It will continue to serve as the backbone of the Russian aerospace forces, not because it is the ideal platform for modern air combat, but because there is no alternative. The Su-57, Russia's fifth-generation stealth fighter, remains a boutique asset with fewer than 20 operational examples as of 2025, a production rate so glacial that it cannot possibly replace the hundreds of aging Su-27 and Su-30 variants still in service. The Su-35S will soldier on, a relic of a different era, a testament to the enduring brilliance of Soviet aerodynamic design and the tragic limitations of a military-industrial complex that can no longer keep pace with its rivals. It is a machine that deserves better than the fate history has assigned it, and that is perhaps the